Hi everyone, my name is Charles Dalland. I'm a PhD student here at the University of Geneva. It's my pleasure today to talk about gravitational wave propagation, even spin non-interactions. This is ongoing work together with my PhD advisor, Lucas Lombrizer, and Pierre Fleury, who is based in Madrid. And so we're going to talk about even spin, that means spin 0, spin 2. So we're talking about scalar tensor theories in the context of cosmic acceleration. So why is it so interesting to study gravitational wave propagation? Well, quite generically, the scalar tensor theories, they are ruled out, except if you have screening. So if you have screening, that means that you recover GR in high density regions such as galactic halos, the blue regions here. So if you look at the gravitational wave geodesic, the production and the detection zone are both in the screening region, and the only region where you can hope to see deviation from GR is in this propagation line here. So this really seems the right place to study deviation from GR. So to be specific, we study a generic scalar tensor theory known as Horndeski gravity, which is defined by these 4 Lagrangian densities. Here you have a scalar field phi, x is the kinetic term. The free functions here, G2 to G5, allow you to recover your favorite scalar tensor theory, such as Brans-Dicke theory, F of R, K essence, the Galileans, but it also allows you to recover GR, for example, if G4 is set to 1 and you have a Einstein-Hilbert action here with the Ricci scalar. So the tensor mode evolution in this theory is given by the following equation, where here you have conformal time, and the deviations from GR lie in this alpha m and alpha t, which modify the friction of the gravitational wave for this alpha m and the speed for this alpha t. And so you may remember in 2017, there was this binary neutron star merger, for which we detected light and gravitational wave only 1.7 seconds apart. And that set very strong bounds on the speed of gravitational waves. So this alpha t is really practically 0, which eliminates most of these terms in this theory, which is great because we have a much simpler theory to study, but the job is not done. There's still G4, G3, G2. Can we learn anything from that? And in particular, there's this alpha m, which depends on G4. Can we learn anything from this guy? So this alpha m is a friction term, so it affects the distance that you're going to measure with, for example, a binary neutron star merger. And this is why it's called standard sirens, because you can build a Hubble diagram from these measurements with combination of redshift measurement. So in this theory, you have a gravitational distance which may not match the luminosity distance that you're going to measure with light in presence of a non-zero alpha m. And if you compute this integral, you will see that it depends on G4 at the time of observation to the time of emission. And you may say, great, I'm going to constrain deviations in G4 for dark energy motivated scenarios where this alpha m recovers 0 at early times, so this integral saturates. And you may say, great, I'm going to constrain this ratio by measuring the gravitational distance. And this was done by many different groups. But this result depends highly on the assumption of a homogeneous and isotropic background. So depicted here, but this is completely unable to account for structure and for screening. So what you have to do is to study the propagation of gravitational waves in a curved background to take this into account. And of course, the fact that you get this result, which depends just on the observation and emission time, you may wonder, is this really a propagation effect? Of course, the answer is no. It depends on the space-time point of observation and emission, which are in the blue regions. So unfortunately, the effect is screened, and the prediction is that in these models, there is no deviation with respect to GR. This gravitational distance is the same as the luminosity distance. And of course, in this result, there are a few assumptions. The first assumption is a weakly curved background. Of course, that's fine in the context of cosmology. And the second assumption is neglecting scalar waves. And that's the typical reaction is, really? Neglecting scalar waves? But you're studying Horndeski gravity, isn't that inconsistent? And so, of course, we had the reasons to make this hypothesis, but it was never really checked that this is really the case, that you have no impact from scalar waves. So this is what we did. And so we studied the equations of motion, we linearize them on top of a generic background. We diagonalize the kinetic term, introduce this auxiliary tensor field F mu nu, define the new gauge, and derive the equations of motion. And here I just display them schematically. So you have the scalar and tensor equations of motion. And you see that there are kinetic, amplitude, mass, and interaction terms, depending on how many derivatives of which field you have. And what is interesting here is that you see, even if you start in a screen region, and you have just a tensor mode which propagates, this tensor mode through this interaction term will source the scalar mode, which will then retroact back on the tensor mode. And then it makes you wonder, is this true? Is there energy exchange between the spin 0 and spin 2 modes? And you have to be a bit careful here because the interaction terms, they depend on G2xx and G3x, the same function that modifies the speed of the scalar mode. So if you consider, you realize that there's this problem, there are three cases. First case, the scalar and tensor mode, they propagate at the same speed, in which case the interaction terms vanish. And that means that there cannot be energy exchange between the spin 0 and spin 2 modes. Done. Second point, the scalar mode travels slower than the tensor mode, in which case the scalar and tensor mode, they get out of phase, and then they cannot interact anymore. Third case, there's the scalar and tensor mode which propagate nearly at the same speed, such that they remain coherent, but then you still have a non-zero interaction term, but however, which is very small. So if it's very small, you can treat the problem perturbatively. And so this is what I did. And I computed the correction to the amplitude of the tensor mode due to this interaction with the scalar waves. And the result lies in this function Q here. If it's 0, it's the same result as without scalar waves. And you see that this Q of lambda depends on the whole integral over the whole geodesic. So it's an integral over the affine parameter of these different tensors which depend on G2xx, G3x, and the background field, phi mu nu, etc. And so, nice, that's an integration, that's a propagation effect because it depends on the whole path in between the source and observer and may accumulate. So we got super excited, and then we said, okay, let's compute for a simple system in a simple model of K-essence chameleon, which can have screening and some non-zero interaction term. And let's see what happens when the speed of the scalar is slightly slower than the speed of the tensor mode. And what we get is that in this situation where you pass close to an ultra-compact white dwarf galaxy, which is motivated by high gradients to make this integral, to maximize this integral, you see that this Q of lambda is extremely small, of the order of 10 to the minus 33. So this might be even smaller than beyond geometric optics terms, which we have already neglected. So, so of course, this effect is really small. So of course, it's a bit sad, but the result is that even if the scalar and tensor mode, they propagate nearly at the same speed, this Q of lambda this correction is very small, and the ratio of gravitational to luminosity distance is very close to the ratio of G4 at the space-time point of emission to the space-time point of reception. And so, yeah, this is the conclusion, that there is no significant polarization or energy exchange with coherent scalar waves. And of course, the fact that the speed of the scalar and tensor mode is a bit different and that you have interactions, you may wonder, is there any analog of Cherenkov radiation in the form of scalar waves? And this is left for future work. So stay tuned and thank you very much. Questions?